I gave myself a starting point, but I really haven't tested it yet. So we'll see how entertaining this gets. So because I don't have my laptop or my virtual machine, we are going to, let's see, where did I put it? I'm using this online GDB thing in a web page, but it should, I tested a couple things. It should let us do what we need to do in here. All right, so everybody can see my screen?
Yep.
Yes, okay. So the idea here is that we're doing the first part of a merge sort, but instead of recursive calls, because remember how merge sort works. I gave you the video to look into it, but this is something all of you should have been exposed to at some point. You have a list of items like this. So in this case, I've hard-coded some elements, 32716. And we ask ourselves, is this trivially sorted? Well, a list is only trivially sorted if it's only one element. So the answer is no, this is not trivially sorted. So what do I need to do? I need to call merge sort on the left half, and I need to call merge sort on the right half. So now we're looking at the left half. Is that trivially sorted? The answer is no, it's not only one element long, it's 3 elements long. So I call merge sort on the left half, I call merge sort on the right half. Is this trivially sorted? The answer is no. So what do? I call merge sort on the left half, I call merge sort on the right half. Is this trivially sorted? Yes, I'm done. Is this trivially sorted? Yes, I'm done. Then we would come up here and we would perform the merge step. Now the merge step was not part of the lab. The merge step is what actually puts the list back together in the right order. So that's where we would say this 2 comes before the 3. We know the merge step that happens here. Here's the return from these 2 calls to merge sort. So 3 is trivially sorted, 2 is trivially sorted, which means when we come back to this level here, the left half of this list is sorted in and of itself, and the right half of this list is sorted in and of itself. Then we would merge them together by picking the winner. So there's like 2 different competitions going. We would say, which is the smaller value, the 3 or the 2? The 2 would be. Which is the smaller value, the 3 or we've run out of things to compare it to? 3 wins by default. So this would get reordered into 2 and 3. And we want to do that inside a shared memory because that shared memory can then be shared by all of the children. Now, when I say the children here, what we're looking at doing in this particular case is instead of recursive calls to merge sort, we're instead going to spawn children. So if we go back and we say, okay, well, here's my original list, and we say, is that trivially sorted? The answer is no, it's longer than one element. So what am I going to do? I'm going to create a child, and I'm going to put him in charge of these 3 numbers, the first half. I'm going to create a second child and put him in charge of those 2 numbers, the second half. All right, so let's just think about from this first child's perspective. This child's going to say, is this a trivially sorted list? It's not. So now this child now becomes a parent of 2 new children. A child that's in charge of that part and a child that's in charge of that part. The child that's in charge of that part then becomes a parent of 2 other children. A child that's in charge of this part and a child that's in charge of this part. And each of those children, that's the end point for them. Because those children say, I've completed my job. I don't have to have kids. It's the end of the bloodline, so to speak. So what we're doing is we're writing the separate, the divide functions of merge sort. We're separate, and we're replacing the recursive calls with spawning children. All right. So what needs to happen then is, let's just use this little example here with this part right here. So we get to the child that was in charge of this portion of the list. We say, is that trivially sorted? The answer is no. So we're going to create a child in charge of this half, and we're going to create a child in charge of this half. So now this child just became a new parent. and this parent has two children that are working on part of the list. And this parent is going to wait for both of their kids to finish before the parent can do the merge step. All right. So after this parent creates the left child and creates the Freudian, creates the right child, it will then wait for both of its children to check back in, letting the parent know that I have finished my sorting. All right. So our goal here is to create enough children so that all of our different portions of our list have been handled. All right. So I've started creating this a little bit and tested this to make sure shared memory and stuff was working in this online environment. And I assume if that's working, fork should work. So I go ahead and I actually hard coded a shared memory ID up here that's just 1, 2, 3, 4. All right, and because I'm assuming my shared array is going to have just 5 elements in it. The size of an int is 4 bytes. 5 times 4 is 20. So the size of my buffer will be 20, and I have 5 elements. So I'm just hard coding some of those things up there. So then inside main, what am I doing? I'm going to go ahead and get my shared memory ID. And then I'll get my shared memory pointer. So I'll attach to the shared memory ID. This will give me the base address of my array in shared memory. Okay, but this is going to be shared memory that all of the children will have access to. So this is centralized memory instead of a pointer to a local thing that each child gets a copy of, but not a direct pointer to the original. So this is going to make sure that there is one array that all the children have access to. And what we'll do is we'll change the portion of that array they're interested in. So what I'm doing right here is I'm just filling up that array with my numbers, 32716. All right, so nothing special here. I just happen to be storing this array in shared memory. Then I'm going to go ahead and I'm going to keep track of what's the current begin and end for this particular process. Now, I've already mentioned that we're going to be creating children here, right? All right, so if we just assume that this first process is in charge of the entire array, that means that they're in charge of bucket 0 through bucket 4. So the top level parent says, I'm trying to sort that. All right, we want a way of reporting that. So I wrote a function here called display that takes in an array and the portion of the array we're asking it to display. So initially we're going to pass in begin to end, which should be the entire array from bucket 0 to bucket 4. So we should get a 32716 displayed to the screen. That's just our proof of concept. All right, so for this particular process, begin and end are those values. And I'm registering with the signal, but we'll get to that in a few minutes. All right, so we're going to test our display function. Just make sure that we can show this array from shared memory from this beginning position to this ending position. So I go up here and I hit run, and we get our array, 32716. Okay, so all we've done so far is loaded up this array. So now we want to ask a question. We want to ask the question, if we're not dealing with the one list. And really, we want to keep doing this. We think about our array up here. As long as we're not dealing with the one list, what do? We split it in half and have spawn a child to deal with the left, spawn a child to deal with the right. We keep doing that over and over and over again, as long as we're not dealing with a one list. Once we get to a one list, like a 2, where the begin and end is bucket 1. So this 2 here means begin is 1 and end is 1. So as soon as we hit something like that, we no longer create any more children. We're just done. That guy's sorted. So we want something to keep happening. So after we display our original list here, we're going to say while begin is not equal to end. So while the portion of the array that this particular process is interested in is bigger than one element, we want to keep doing something. All right, and what do we want to keep doing? Well, we're going to have to keep track of the beginning and end of the first half and the beginning and ending of the second half. So int begin 1 is going to be equal to begin. Int end 1 is going to be equal to, now this is the trick with merge sort that I hope you remember from when you previously have learned merge sort, is how do I calculate the end of the first half? Some people might say, well, don't you just say n divided by 2? Now that would work initially, right? So if the first half is 0, 1, 2 here, and end is 4, 4 divided by 2 gives you the 2, that seems like it's right. But what if you're looking at this portion of the array, buckets 2, 3, and 4, and you're looking for the end of the first half, which should be 3. 4 divided by 2 gives you a 2. So it doesn't actually give you the right value. The math for calculating the end of the first half is end plus begin divided by 2. So 4 plus 0 divided by 2 gives you 2. 2 plus 4 divided by 2 gives you 3. So on and so forth. Okay, so end 1 will be the end plus the begin divided by 2. Begin 2 will be equal to end 1 plus 1. 1 past the end of the first half. End 2 is equal to the original end. So what are we doing here? This is left half is those guys, and this is right half. All right, so we've just created some local integers that keep track of where the beginning and end of the left half is and where the beginning and end of the right half is. And now what we want to do, we're only inside this while loop. If we are a process that is not looking at a portion of the array that is one element long. Hold on. Misspelling in my while statement. Oh, thank you. Begin not equal to end. All right, so left and right half. So I'm only inside of this while loop if I am not looking at a one list. That means my begin and my end are different, which means I need to create two children. Two. So instead of two calls to merge sort, like we would historically have done this with recursion, I'm instead going to spawn a child. So let's do that first. So we'll say int PID is equal to fork. So we'll go ahead and we'll get a copy of this process. And remember, that copy is going to have access to begin to end, begin one, end one, begin two, end two. But they're getting a copy of all those things. That's something we explored last Wednesday. All right. And they will have access to the shared memory. And this is the thing where it wouldn't have made a difference for this lab because we're not actually changing the array. That's the merge portion of this that will happen next. But for the lab, I went ahead and put it inside of shared memory because ultimately, when we merge these things, which is actually where the sorting takes place, we'll be wanting to change the original location of our list, not copies of the list that the other children won't be able to see. So that's why we've put our integer array inside of shared memory. Okay. So all the children will get copies of this pointer. We saw last Wednesday that the pointers are the same, but they were inside of like a protected memory pod where it was relative to the beginning of a process. Where if I'm using shared memory like this, the pointer is to an actual place given shared memory ID. So now this only exists one time, not one time per child, but one time period. So this integer array will exist in a centralized location. All right, so we're in here. We know we're not a one list. We figure out where the beginning and end of our left half is. We figure out where the beginning and end of our right half is. Then we go ahead and create a duplicate of ourselves. We ask if PID is equal to 0. If I'm the child, we'll say I'm the left child in this case. So if I'm the left child in this case, what do? Well, I'm in charge of begin 1 to end 1, that portion of the array. But this loop that I'm in operates off of begin and end. But I have my own copy of begin and end. I have my own copy of begin 1 and end 1. So I can go ahead and say begin is equal to begin 1. I'm a brand new process. I'm the left child. If we just want to think about this geographically, I'm the left child. So from my perspective, begin is begin 1. End is end 1. That's the portion of the array that I'm going to be dealing with. Else, and what I can go ahead, well, actually, we'll do it here in a second. Else, if I'm inside here, what am I? I am the parent. Well, so if I'm the parent, what do? I create a second child. If PID is equal to 0, I'm the right child. So begin is equal to begin 2. End is equal to end 2. That makes sense? So if I'm more than a one list, figure out where the beginning and ending of the left and right half are. Create your first child. If you're the first child, your begin is actually begin 1, your end is actually end 1. Otherwise, you're the parent, create a second child. If you're that child, you're the right child, your begin is actually begin 2, your end is actually end 2. Else, I'm the parent waiting on their 2 kids. So I'm probably waiting for a callback. I'm probably waiting for a signal. So I'm going to go ahead and say I'm going to pause. And really, I'm waiting for a signal twice. I want each child to let me know that they're done with their portion of the array. So if I'm the parent, after I've created my left child and my right child, I'm going to wait for a signal, because this parent can't continue on until they've received, in our case here, 2 signals. They've received a signal from the left child saying I'm done, and from the right child saying they're done, so that this particular parent can say, okay, I know the left half of my list from begin 1 to end 1 is sorted. I know the right half of my list from begin 2 to end 2 is sorted. So now I can go ahead and do the merge step now that my children have done their job, presumably, and their children's children have done the job, and so on and so forth. All right. So a parent's job is, if they're not a one list, create a child to do the left, create a child to do the right, then wait. All right. And let's see, we can go ahead and do it at this level because the parent here is not gonna. So we're going to go ahead and call our display. So I'm already calling it display from begin to end. So I can actually just do that right here at the beginning of my while loop. So when we enter this while loop, regardless of which process we're in, When we enter this while loop, we're going to display the portion of the array that we're interested in. So the very first time in here, we're showing from the real beginning to the real end. This will be 32716. If I'm the left child, the next time through, I'll be showing the 327. If I'm the right child, the next time through, I'll be showing the 16. Because the left and right child update their version of begin and end to be equal to either begin 1 end 1 or begin 2 end 2. That's what we're doing in here. If I'm the left child, I set begin to begin 1 and end to end 1. If I'm the right child, I set begin to begin 2 and end to end 2. Any way you cut it, what's the very first thing I do inside this while loop? I show the portion of the array that I'm dealing with here. Now I'm going to go ahead and steal that, because if we don't get into this while loop, if we bypass this while loop, that means begin and end are the same. And if begin and end are the same, we want to go ahead and display that portion, right? We want to display that portion of the list, which is going to be things like 3 or 2, because when I'm just looking at this portion of the list, bucket 0 to bucket 0, begin and end are the same. So I won't actually do a display inside this while loop because I didn't get into this while loop for that particular child. Okay, so this has to be us, remember how difficult recursion was to grasp, and probably some of you still find recursion pretty difficult. Now you're saying, well, I'm going to replace recursion to actually creating actual other processes, child processes, to do the work that I would have done recursively before. And the advantage of that is now your recursion doesn't block. You can have multiple children all working on a portion of this problem. And as long as they're working on their little part of the world and their parent who can't do the rest of the job until their children are done, they can be working on the entire list or portions of the entire list simultaneously, rather than having to wait for the first recursion call. Well, with merge sort, you have 2 calls to merge sort, right? And the original second call to merge sort won't happen until the entire left half of the list is sorted. And depending on the size of the list, that could be a long time, because that could be hundreds of recursive calls later. Whereas if I'm creating a child to do the left and a child to do the right, the left and right have nothing to do with each other than eventually the original parent will be merging those 2 sorted lists together. But the left and right half of the list can be working completely independent of each other in terms of their sorting. So it doesn't have to block. So we're bypassing the concept of blocking here.
Does it also prevent Stack Overflow errors?
Well, it would prevent Stack Overflow from the perspective we're no longer calling recursion. We're calling things recursively. Recursion uses the stack, right? When you call a function, so recursion is when a function calls itself from within itself. When you call a function within itself, it puts the current function on hold. It pauses it and creates a brand new duplicate of it, pushes it onto the stack. In this case, our manual pause, this is just saying, I'm the parent, I cannot continue until both of my children have finished their job. If you want to think about this in real life, let's say that I'm making we're gonna come up with a 2-ingredient. We're making a ham omelet. I'm gonna need eggs and I'm gonna need ham. So I'm gonna go ahead and send 1 kid to get the eggs, and I'm gonna send another kid to get the ham, and then I'm gonna wait. I can't start making this omelet till my kids come back with the eggs and the ham. I need my children to finish their job before I can continue with my job. That makes some sense? So that's what this pause is doing right here. Pause is our system call for saying, I'm waiting for a signal. And that signal is ultimately going to come from the children. We're not actually sending that signal yet. Because right now we're just doing the division part of this problem. The lab was just to do the division, not to actually do the sorting. All right. So the parents done their job. They've created a left child to work with the left half. They've created a right child to deal with the right half. And now the parent just waits for their kids to fulfill their purpose. All right. And we're going to keep doing this over and over and over again until we finally end up with a process where begin and end are the same. And that person, that child, will just display that portion of the list and be done. They're not creating any new kids. This is the end of the bloodline, right? Because they don't need a left half and a right half to be sorted. They are a sorted list. This child got it easy mode, right? If you're that child who was handed, scroll, handed bucket 0 or whatever it was. What is this? So here, bucket 2, 3, bucket 3 to bucket 3. You're this child right now where your begin is 3 and your end is 3. You're saying, ha, I don't have any work to do. You gave me one element, and one element is by definition already sorted. It's already in order. So I'm just going to presumably send a signal back to my parent saying, I have finished my job. We're not doing that yet, but that's what you would do because we don't need this child to do anything else. This child doesn't create new copies of itself. It's hit the bottom. Okay, so our goal here is to have each process show the portion of our list that they're in charge of. The original parent's in charge of the entire thing. One of the children's in charge of the left half. Another child is in charge of the left half of that. Another child's in charge of the left half of that. Another child is in charge of the right half of this guy. Another child is in charge of the right half of this guy. Another child is in charge of the right half of this top level guy. Another child is in charge of the left half of this guy. Another child is in charge of the right half of this guy. Okay, so we want these children to advertise to us the portion of the array that they're in charge of sorting. So what we'll do inside of our while loop here is we'll just keep displaying this is the portion of the array I'm in charge of over and over and over again. And then as soon as we break out of this while loop for one of the children, when he's only dealing with the one list, he'll go ahead and say, here's my one list. So this will always just be a one thing. So there's our 32716. That was the original parent. Here's left child, right child. Actually, here's something interesting right off the bat. I mentioned that if we were looking at merge sort under normal circumstances, that right half, this 1/6, this would have to wait until the entire left half was done. But notice, because of the way these processes are being scheduled, the right child here, 1/6, he's actually creating his left child ahead of the original left child creating their left child. So this is the right half's left child right here, this 1. And that actually happened before the original left child's left half. And here's that child's left half. Here's the right child's right half. Here's the right child's, was that left half? No, right child's right half. This is the right child. This is the left child's right half. That's where the 7 came from. The 6 is the right child's right half. And then the 2 is the left child's left child's right half. So that covers all of the children. All right, so that should be it for the lab. So we don't have any recursive calls. All we're doing is working with the copies of begin and end that we got and updating begin with the appropriate begin 1 or begin 2, and end with the appropriate end 1 or end 2 for the portion of the list that this child was in charge of. Now, one thing we do have going on here is right now, this program is actually still running. Why is this program still running? We've got all the output we were expected to have, right? This is all the correct output. But why is this program still running?
None of the kids are killing themselves.
Actually, all the kids kill themselves. Oh, well, all the final kids kill themselves. These are the easy street kids right here. They all kill themselves. Well, I mean, they kill themselves so far as their program naturally ends, right? These are the kids who only have one list to deal with. But any kid who had a 2 list or more to deal with is currently doing what?
It's paused, and then we're not sending the signal that it's waiting for.
On their kids, right? So if you were one of the unfortunate children who had work to do, because these are the easy street kids, right? You were born into a life of luxury where you only had a 1 element list that you were supposed to sort, and you're just sitting there sipping pina coladas without having to do any extra work. You broke out of this while loop. You didn't have to spawn a left and a right child. You're just done. And you just, spit out to the world. This is my 1 element that I was in charge of. I'm done. But what happens is any of our children that then became parents. So if they were inside of this while loop, those parents are waiting for something. They're waiting for their children who have finished sorting, to ultimately let them know. So this child, I gotta stop it because it is running. So this child right here, this child has finished sorting by default. So they need to let mom know they have completed their task. Now, at this point, this isn't even part of the lab. The lab, you could have finished right now. We have all our right output. We've proven that we have children in charge of all the individual parts of our list. All right. But presumably this child right here, easy street kid, he has decided, you know what? I am actually completely done sorting. I didn't have to do any sort of special stuff to sort. So now what I need to do is I need to just let mom know that I'm done. So I need to send a signal to mom. What function does a process use to send a signal to their parent? This is our understanding of the difference between raise and kill. If a process wants to send a signal to their parent, do they use raise or do they use kill?
You'd use kill, and then you do like get PPID, and then you'd probably do like a comma, and then whatever signal.
Now, just as a reminder here, I know I kind of skipped this earlier, but every single process here did register themselves with the handle SIGINT. So they've all registered themselves given that process ID. Actually, can I do it there? I think I actually need to do it here. So before a parent pauses, if they know they're going to have to wait on their kids, they're going to go ahead and register themselves to be interested in some signal. I'm going to use SIG interrupt here, but you can call it SIG user 2 if you want. It doesn't really matter. which signal you, so we could do sig, what is it, sig, US, we'll just do sig interrupt. All right, so we're gonna, this parent saying, I am interested in sig interrupt, and I want to call this function when sig interrupt happens. And then they wait. So in this case, a child has finished their sorting. Trivially finished their sorting. So they're going to go ahead and send the use kill to send a signal to their parent. So this is get PPID. That's their parent. That's who they're sending the signal to. And the signal they're sending is SIGINT. Okay. So now I'm trying to scroll. So here's our signal handler. So this signal handler, we've received a signal from one of our children. Now, any parent in our example here has exactly 2 children. That's how merge sort works. If you either have 0 kids or you have exactly 2 kids. So you would only be getting this message if you were a parent waiting on your kids to finish their job. So we're going to say printf parent received signal from kid. We'll say %d here. We'll do a \n. Now we want to know the kid that sent us the signal. So that means that our parents int kid number, originally they have 0 kids. All right, parent originally has 0 kids. If we want, well, we'll do a countdown, I guess. It doesn't matter. This will work fine. So a parent originally has 0 kids. So we'll go ahead and say we've received a signal from kid number. And then we'll say kid number ++. Because this parent is only going to do anything once both of their kids have finished. Are both kids done? If so, the first kid came out, a 0 became a 1. When the second kid calls, a 1 becomes a 2. So if kid number is equivalent to 2, both kids are done, and I can now merge the 2 partially sorted lists. Else, if this was if only one of my kids are done, what do? For instance, if only my left kid has reported back and said, Mom, I'm done sorting, what does this parent then have to do?
Would you just pause again so you get?
Yep. They have to wait on the right kid. Wait for the other kid to finish. So that's what this parent will do, is pause. Otherwise, we can do a print f time to merge. And then put merge code here, hint. And then once we're done merging, we'll go ahead and we can have this parent finally exit. They've completed their task. All right, but before they complete their task, this parent has to let their parent know that they finished their job. And how do we do that? They contact their parent. So even though they were a parent themselves, they were also somebody else's child. So they say, Mom, I have finished merging. I've finished sorting the portion of the list I was in charge of. So I want to let you know that I'm done. So their parent will receive a signal working off of their current count for kid number. Remember, each child is going to get their own copy of these variables. They're going to get their own copy of these variables. So they're going to be keeping track of the kid numbers that are associated with this. And actually, if you want to make sure that you're safe with all of this, you can say kid number is equal to this. Starting it off, it's, you can just start it off as blank. And then right before you create each child, you set kid number equal to 0 for that child, just to make sure that they're getting the right starting point for the number of kids. This protects us from any sort of race condition situations. So when they create their first kid, they just make sure kid number is 0, which it should still be, because this parent, they can't have a kid report back to them if the kid hasn't finished their job. And if the kid's not being born until right here, you're probably pretty safe. But just to be extra safe, we'll say, look, I'll go ahead and make sure that this kid is born with a variable for kid number equal to 0. Similarly, I'll make sure my other kid is born with a kid number equal to 0. Presumably, it should still be 0. I'm just ensuring that my kid number will be equal to 0 beforehand. All right, so that means that each process that was born is guaranteed to start off with a kid number value that is 0, which means that for every child who becomes a parent, this function would have to get signaled twice in order for them to come in and do their merge. And once they do their merge, they will go ahead and then send the message to their parent, letting them know that they are done with their part of it. And then that child can exit. Make sure So here's my signal handler. I received a message from kid number, from kid 0. I'm going to say kid number is equal to, I want to say this is a problem with that plus plus operator. I kind of remember mentioning that maybe last class, last Wednesday. The plus plus operator was not always defined for C. So kid number is equal to kid number plus 1. If kid number is 2, go ahead and do your merge stuff because you've heard back from both kids. Otherwise, wait. Kid. Misspell. Which one's right? Capital Ed. Kid numbers are not going up. Parent is still waiting. need to start off at 0. It's not finishing because it's not getting the second kid. Kid number 2 is never sending. So if I'm a parent to register my handler, I wait. As soon as the kid is done, we fall down here. The kid displays their thing. They send the kill command to their parent. Parent receives the signal. Some kid number, and all the ones we've seen have been 0. So 0 becomes 1. 1 is not equal to 2, so we get into the else where we wait. The other kid finishes, sends it back. Kid number should be a 1. 1 becomes a 2. We're equal to 2. What do? We print time to merge. Then we call our merge code.
Is it because
and
you're pausing inside of the signal handler?
It shouldn't be a problem. That should be allowed. Because we need to pause again. That's what the parent here does. So if the kid number is equal to 2, do this stuff. But if it's not equal to 2 yet, the parent has to wait for the other kid to finish. So let's go back into pause mode. We just do a print F. Current kids is equal to %D \n kid number. So we should get 1s out of that, proving that it is increasing. Current kids is 1. So it waits. Might be shooting myself in the foot with this. I think I'm resetting it for. I think we start with it at 0. We send the kill command here. That's when that child is done. That's at our 1 list. So if we go from the bottom up, that child then sends to both of their parents. The kill, but that parent doesn't act upon it until they've received 2 different things. So it's something with this kid number variable that we're not incrementing correctly. So that's okay. We're right at the point where we're ready to do our merge. So we'll come back on Wednesday and we will write our merge step in here so that in the end, we should have our final parent get the notification that, okay, you can do the final merge. We'll merge it back together. And then we have a fully distributed merge sort without using recursion. All right, so questions, comments, concerns about the things we did today with having the 2 children per parent who dealt with something larger than a 1 list. Okay, I will see everybody on Wednesday.
Thanks, Whitman.
Yep.
Thank you.